Okay, let's get started. Today we're not gonna talk about, we're not gonna continue to talk about machine learning. We're gonna take a break. Today we're gonna talk about fractal design, fractal learning, and fractal intelligence. So, because it's the weekend and I don't wanna give you a headache with machine learning and deep learning, so we're gonna take a break and talk about the fractal design and how to apply it on Grasshopper and Unreal Engine. Okay, so let's get started. Okay, what do you know about fractal design? Have you ever heard about this term? Does anyone heard about fractal geometry or fractal design?
Yeah, I think it repeats itself and creates a pattern.
Yes, thank you. So the fractal design, it's like a geometry. It's based on a mathematical equation. It got repeated over and over through the fourth dimension. And you know what's the fourth dimension, right? It's the time. So it's an infinite loop of that repeating. So it's a pattern or geometrical pattern that gets repeated over and over through the fourth dimension. So it is geometric shapes containing detailed structure. So once you zoom in, you find details. You zoom in more and you find more and more detail because it's repeated over the fourth dimension. So it's a detailed structure and usually have a fractal dimension. The fractal dimension is what we call it the fourth dimension of the time. It gets repeated, strictly exceeding the topological dimensions. What's the meaning of all that? It's a pattern that is repeated over and over through the fourth dimension. It's an endless pattern. So this is like an advanced technique to reach patterns using mathematical equation and using computational designing. That's why I'm getting through it, because once you get into deep learning, you're gonna face a lot of deep neural network, a lot of hidden neural networks. So you have to know what to do with it, because once you reach a complex neural network, it's like impossible to understand what the machine is going to learn or to train. Okay, so you have to understand something called the fractal learning. It's when you go, or the fractal intelligence. It's when you go to the main system without getting lost in the detail in the subsystem or the sub-hidden neural network. That's what I want. I want you guys to know more and more about fractal geometries or fractal design, the concept or the mindset of the fractal geometry. So let's see an example for that fractal geometry. So we do have like a curve, and this is called the Sierpinski triangle. You see, every iteration it gets repeated over and over until it reaches like the highest detail or the highest pattern of that geometry. Is it clear to you guys? If you notice, in the first we started, my computer crashed. Okay. I don't know, it's crashed from PowerPoint. Okay. Let me just go again. So if you guys see, at the first we start with a simple curve that present a triangle. Then we get to divide that triangle over and over which we call it over the fourth dimension. So it get divided over and over until it reached the highest detail of that triangle, and we call that Sierpinski triangle. So what's the fractal geometry models? We've heard, I don't know if you guys heard about Mandelbulb. Have you ever heard about Mandelbulb? Yes, Mandelbulb and Julia bulb, it's a type of pattern that goes to the third dimension. What we've seen before in the video, it's only in the 2 dimension, and it's repeated in the 4th dimension, which is time. But Mandelbulb and Julia bulb goes with the 3rd dimension geometries, okay? And you know the snowflake and the L system trees. Have you ever heard about the L system trees? Every architect knows about the L system trees. And last of all, the Mandelbrot. The Mandelbrot, which is the 2D version of the Mandelbulb. So which software can we use to achieve this type of fractal geometries? We could use the processing software. It's called processing, and you can write a code with the Java, I guess, and Python. We've heard about Houdini, side effects, Houdini, and Rhino 3D. Rhino 3D, yes, if you know Anemone or the for loops, and if you know C# and other programming languages. And we could do that with the Autodesk Maya as well. So this is the Mandelbulb. Maybe you've seen it before and you don't know the name of it. This is the Mandelbulb. So it generates pattern and detailed pattern over the 4th dimension. And the original shape of that Mandelbulb is, like you know, it's a sphere. So we're gonna go and try to generate a Mandelbulb through this session. So let's try to do that on Grasshopper to generate a fractal geometry. We're gonna start with the Grasshopper, then we're gonna move forward to C#. Okay? Who doesn't know how to program in C#? I believe everyone knows how to use a C# component inside Grasshopper, right? At least the fundamentals, not in details. Okay, let's get started. We're gonna go through the Sierpinski triangle, and if we go and search, yeah, we're gonna go through this equation in the Mandelbulb. But if we're gonna Sierpinski triangle, and we find that pattern, and we're gonna achieve that pattern or that fractal geometry using the just the regular Grasshopper component with Anemone. Okay, let's get started. Okay. So Sierpinski starts with the pyramid, or let's say pyramid or a triangulate face. Okay, so in order to achieve Sierpinski triangle in 3rd dimension, we're gonna start with the pyramid. We're gonna like construct a pyramid and start with it. Okay. Then we're gonna reference that inside that geometry inside Grasshopper by using the BRIP container, right click and set one BRIP. And how many faces does that permit have? Technically, yes, thank you. It's 4 faces. We have the sides and we have the bottom. So we're gonna take and subdivide every face to different or like mini triangle, and then subdivide these faces into another group of triangles. So we're gonna take that face and we're gonna use the lunchbox generate and let's say subdivide triangle. Sorry, we need the faces first of all because it takes, I guess, curve or surfaces. So we're gonna deconstruct that burib and take the faces. And it's going to give us this type of subdivision. But here in the number of subdivisions, it says 2, we need 1, and we're gonna repeat that over and over. So we provide the number of subdivision, which is 1, and that would give us the exterior structure of Sierpinski triangle. If we go to see it here, we have like 3 main triangle and they get divided over and over through the 4th dimension. So we have the structure of the Sierpinski triangle. These triangles are curved and we're gonna convert them into surfaces in order to repeat that pattern. So we're gonna use boundary surface to get those surfaces like you see here. Okay, and each one of those faces has like 4 triangle, 1, 2, 3, and 4, but we don't need the middle one, okay? Because like you see here, we don't use the middle one for subdivision, only the 3, the remainings. So we're gonna avoid that middle triangle and we're gonna search for it. If we use list item to see which one, we can see that the middle one is the first index or the first element of that list. So in order to eliminate that item, we're gonna use the call index, call index. Call index just remove or cull the indices of the elements from a list. So we take that list and we're gonna remove the first index, which is 0. So we're gonna have 3 triangle here. Okay. Now we're gonna make like 4 different pyramids. So in order to do that, this is we're gonna need to weld or join all these surfaces together and cap that face in order to start the subdividing or dividing that pyramid. So in order to do that, we're gonna flatten that list and we're gonna use join, pyramid join, sorry. and that would give us 4 open VREPs. The first one, the second one, and the third one, and the fourth one. So if we look, we're gonna find 4 open VREP here, and we're gonna cap these rows. See, now it's a closed VREP, and we're getting back to the first initial geometry that we have. So fractal design, basically it's a repetitive pattern of that procedure or that process. So in order to reach that, we're gonna just repeat that. Sorry. Like over and over to reach that pattern in the third dimension. Okay, so it's not efficient to do that, to repeat these components over and over. We're gonna need a loop inside Grasshopper, and in order to get a loop inside Grasshopper, we're gonna use Anemone component. Anemone component helps you to have a loop inside Grasshopper without needing to write it in programming languages. So we're gonna have the loop start and the loop end. Okay, and the first one goes with the first one and the other component. So the body of the loop goes here, and the initial parameter goes in the first. So the first parameter goes there, and the body keeps, and the loop keeps going over and over with the number of repeats. Okay, so the first parameter here we have is this one. Let me just hide these. And we're going to repeat that process inside the body loop. So we give it as a reference period. Now we can get it from here and give it back. So we're gonna just copy and paste these. And the number of loops 0 in order to give us good. And this is the reset trigger here. We can reset the loop over and over. So let's repeat that process. And we need to provide like an individual branch for every pyramid here. Sorry. Each pyramid here will go individually for subdivision or the generating of that pattern. So we're gonna graph this list and provide it again. So each branch will go individually here. Okay, let me just hide this one and hide this one. And give me output last. Okay, we need the latest output from that loop. we're gonna flatten and have it here as reps. Now once we repeat that, you see it goes on and on to an infinite loop. So we had first basic or main pyramid, then we go to the second one, then we go to the third one, then the fourth one, and so on. Is it clear to you guys? This is like a basic example of the fractal geometries. Does anyone have any question? Okay, now let's move on to the second example here, and we're gonna talk about the Mandelbulb. The Mandelbulb is like more complicated than just a Sierpinski triangle, because we're dealing with a three-dimensional grid, and that three-dimensional grid gets subdivided over and over through the fourth dimension. So if we go back here and read about the Mandelbulb, it's three-dimensional fractal, and it goes in the fourth dimension, and it uses bicomplex number, which means we use like a complex equation in order to reach that shape. And as you can see, we have the velocity and we have the round of each or the length of the vector. We have phi and we have theta. Okay, so we're gonna apply this equation inside a C# component in order to reach that pattern. Hopefully we will reach only the vertices of that pattern, because a Grasshopper and Rhino, let's say Grasshopper doesn't support a GPU computing, so the component might crash after the third or the fourth iteration. So let's get started with this shape. Okay, let's get started. So in order to have this equation, we're gonna use the math library from the system, and we're gonna use a C# component. And we're gonna need the number of iterations, and we're gonna need the scale or the multiplication for this vector in order to expand the vertices over and over from the center. Also, we're gonna need the points, list of points, point 3D here, and these type of geometry, these type of variable are gonna be integers, and we're gonna need a spherical grid. And how to achieve a spherical grid? We have like two options. We could get the mesh sphere here and get those points and apply them into the points here, or we could just have a sphere and subdivide it into multiple points. Okay. So we could use both ways. Okay, let's say here 5. And the number of vertices are gonna represent the resolution of that geometry. So more vertices, more resolution. Okay. Now we flatten these points and give it to the I points. I for an input and point, which would take a list of point 3D. And the scale is going to be 3. The number of iterations, let's try with 1. And let's get started. Okay. First of all, we're gonna define the direction or the vector, the vector, which will be here as the length of the movement or the displacement of these points from that grid, the vectors. Okay, so we're going to start with the list, and the type of that list it's going to be the vector 3D, and we're going to name it as a vec with the new list vector 3D. Okay. So now we're gonna copy all the points here from the I point to the vector list, from the I point list into the vector list, and to do that we're gonna use for int I equals 0 I plus. Okay, so we're gonna start a for loop to get all the data of the or the coordination from the point and copy it into the vector list. And in order to do that, we're gonna start a for loop from 0, and I, that integer, will stop when it's less than the list length of that list. Okay, which we call it iPoint.count, the number of the items inside the iPoint list, and the increment here, it's a plus. Okay, so we're gonna say vector.add that's going to be the I point I dot x, okay, and the I point when the index is I dot y, and I point okay, we're gonna copy the coordination from the I point on the index I, which is 0 by the first loop, then the Y coordination and the Z coordination into a new vector inside the Vic list. Okay? And we could always present that as a vector here to see as an output. Okay, let's move on. Then we're gonna define the length of every vector. Every vector here has a length. We're gonna define it as a double list, which is a round number. Okay, we call it R with the new list as a double here, and we're gonna define a copy from the original I point list. So we have a new list. We call it point 3D, and we're gonna call it a copy point, which equal a new list point 3D copy from the I point. Okay. Then we're gonna start the fractal loop. So for I0, I scale, which is the multiplication of these points, I plus plus, okay. Then we're gonna get the length of every vector we have in that list, and in order to do that, we're gonna use for each a vector 3D, we call it V, in the list of vec. Please add r dot add the v dot length. See here, computes the length or the magnitude of this vector. So we're gonna get the length of from the vec list, and in order to test it, we can just write a, which is the reference output here, as an r, and call it. See, that will give us the length of those vectors. Okay. Now we're gonna start with the equations and defining the definition of the phi and theta and the velocity and everything. Okay, so we're gonna start a for loop inside a for loop. So j equals 0 and j, and this loop must stop before reaching the number of vectors count, which is the length of that list, and j plus plus, which is the increment of increasement. So let's get back to the equation and see. we have the phi and we have the theta. Okay, y over divided by x. So let's start with the phi. Double phi equal math dot and which is the arctan of y over x, which is the y, the coordination of the vec on the y axis and the coordination of the vec on the x axis. Okay, so we're gonna write here. You can see here a double y and double x as an input variable for that. We're gonna take the vec on the j and y over vec on the j x. That's for phi. Okay, you see here vec arctan two variables, sorry, y over the x. We're gonna move to theta, which is the square root of the power of x plus the power of y divided by z. So let's get back here and double theta is equal to math dot theta the square root, the power of 2, okay, math dot square root and the square root of, we could use math dot power, which is the power, or we could just multiply with itself. Okay, and in order to simplify that, I'm gonna multiply with itself. Dot x multiply with itself dot x. Okay, then plus, I guess. Yes, here also the multiplication of y. So we have now the vec of j dot y multiplied with the vec of j dot y, and that's for the square root, and we have it all over the z coordination, which is that one, and the z coordination. So we have the arctan of the square root of x multiplied with x plus y multiplied with y, which represent this one. And the second part is the vector on the index of j, of course, on the z. Okay. Now, if we go back, we're gonna start with the VR, the velocity of r, and we're gonna start the vector of r and the vector of x and the vector of y and the vector of z using phi and theta here. So we're gonna get back and define the vector of r, which equal math.o, which is the r and the j, the length, powered by the n, which is the iteration or the number of loops. We have double dx, which equal yes, this one, this one, sine multiplied with the cosine and the sine multiplied with the sine, theta and phi, and last of all is just theta. Okay, so math sine, which is the iteration or the number of loop multiplied with theta, and all of that multiplied with math dot cosine, which is n multiplied with a phi. Right? Yes. The theta multiplied with phi. Now for the y, we have the sine of theta multiplied with the sine of phi. So if you go back, and we have double dy of sine, which is n multiplied with theta, and all multiplied with sine, which is n multiplied with the phi. And last of all, we have the Vz, which is a cosine of n multiplied with the theta. Here, sorry. Okay. Vz math dot cosine, and it's n multiplied with theta. Okay. Now we're gonna assign the new vector of the Vx and Vy and Vz into the list of vec. So j equal new vector 3D. It's gonna be the Vx, Vy, Vz here, and multiplied with a VR, which is the length of that vector, plus the position of the point. Yes, vector 3D, because it's a point, we have to assign that. If we don't assign it and write down the copy of the point over the J, we're gonna get an error here, because the type of the vector is a vector 3D and the type of copy point is a point 3D. So we might get an error. Sorry, it's CPTS. We'll get error. Are you missing a cast? We're gonna cast that to convert it into a vector 3D to avoid that error. Then we're gonna update the position of that with the new vector that we have constructed here. We're gonna update the position of the copy points. So we say vec, which would give us the we're gonna update it with a new vector. Okay. Now let's see these points. A equal C plus. Okay, so a small scale up to this scale. Okay, we're gonna hide this one, and we're gonna start the iteration, and the loop is going to happen here. See? Let's make it 100, and we're having the shape of Mandelbulb as a vertices. And since we don't have a volume 3D inside Grasshopper or inside Rhino, Houdini does, but in Rhino we don't have, so feel free to like represent these points with the geometry like you want. And we could represent it with a surface, but it's not efficient to present it with a surface. Like we could construct that surface from points if you want to, and have the U count here with the expression of +1. Okay, but I don't recommend it because it's not coefficient of the Mandelbulb here. See. Is everyone still alive, or you guys okay?
Yeah.
Yeah, I know it's like a hell of processing since this is our first time we are using a programming language, but it's fun to play with, especially with the Fractal. Is it understandable for you all? Now you could take this coordination and apply it on a voxel. I don't know if I have it here. I hardly think so. Do you know the voxel? Do you know the voxel, guys? Yes. You could apply the voxel. Voxel, let's say pixels. You see these voxels here. It's the 3D pixels. Okay? For each point can take one pixel and apply it in a 3D geometry or 3D space. So you could have it as a mesh, then smooth and flatten that mesh over and over to get like a smooth output. So this is the voxel. You could apply it. I don't know if I have it here on, I hardly think so if I have it here on Grasshopper, but I guess, guys, you could reach the voxel and show it to me. Okay? Does anyone have any question? Now you could just try to do that. It's not like an assignment to do the cubic formula here. You reach that cubic fractal of Mandelbulb, and these are the equation for the cubic formula or the quintic formula as well. You could try and just show it to me. The idea here to apply mathematical equations inside Grasshopper, because in the future we're gonna face a lot of like a machine learning equation, a lot of complex equation, and we need to break it down and apply it in our machine learning, or to train model in it. Okay, so let's see these detail inside Unreal Engine. Okay, so once you go to github.com, let me just sign in here. Once you go there, you're gonna find in my repositories a Mandelbulb. This is the component that I've written earlier, and this is the source code if you wanna convert it into a plugin, and this is the Mandelbulb for Unreal Engine. Okay, just download the zip file. Okay, once you download it, you're gonna have the Mandelbulb main. Okay, so once you have the Mandelbulb main, just extract here the folder and get that folder inside. So let's launch the Epic Games. Everyone knows how to use Unreal Engine, right? Does anyone have a problem with it? Hopefully.
I've never used it so no.
I'm sorry?
I haven't used it. I know of it, but I've not used it.
Okay. Let me simplify that. Okay. You go to Epic Games, to their main website. You download their launcher, and you make an account on your Epic Games, and then you go to library and install a version which we call it 5.0.2. Okay, just install it on your local hard drive. Once you install it, just launch the Unreal Engine. Oh my god. The fan of my laptop. Sorry. Does it bother you guys, the fan? Should I turn it off?
We can't hear it. It's fine.
Is it now better? Okay. Now, once you open the Unreal 5, go to the games, choose a blank project, name it like Mandelbulb. You cannot use spaces, or we call it white characters, inside Unreal because it's based on C++. So I cannot use spaces, okay, inside Unreal Engine at all. So just name it Mandelbulb, or name it whatever you want, and we're gonna use a blueprint, and we're gonna create our first project of Unreal with Unreal Editor. So let's dismiss and choose update. Now, for moving inside the Unreal, or to navigate inside the Unreal, just keep clicking on the right click and move with your WSAD, just like a game. Okay, so in order to move up and down, we use E and Q, and to move around, we use the mouse, and forward and backward, we use the WASD. Okay, after that, we're gonna go and to our main, where we saved our Mandelbulb. We go to the Mandelbulb, or the name of your project. We go to the content here, and we're going to paste that Mandelbulb folder here in the content folder. Okay, just paste it, and you'll notice that it appears inside your project. Okay, now the orange line here means it's a level. It opens a scene for you. Okay, The light blue, it means a geometry or a mesh. As you see, it says static mesh. The green one, the light green, it's a material, and the dark green, it's a material instant. So once you apply that inside, you're going to see your Mandelbulb is ready. And because it's based on the Unreal is based on the GPU computing, so it doesn't take long time to reach that Mandelbulb. Okay, now in order to play with the iteration and everything, just click on the Mandelbulb instant and a window is going to pop up and show you your Mandelbulb or your geometry. We could control the color offset of that Mandelbulb, the period of this coloring, and we could choose a gradient for the coloring as well. We could choose a specific color and the hue shifting between these colors. Okay, now we don't use emission here. Okay, so we don't need to use it. Now we could use the fractal parameters. So you see here more fractal, it's more depth in the detail. Let me just minimize and slow the camera. You can slow the camera from the camera speed here, perspective. Let me slow it and see. And to full screen, to maximize the perspective, just hit F11, and you could use and see. Okay, let me just scale it up. In order to scale it, we click on the R on the keyboard and it's going to bring up the scale, or we could use the scale button icon. Okay, so we can scale it up like that to see the pattern of the Mandelbulb. And to move it, just click on W and you can move it. And to rotate it, click on E and you can rotate it. Okay, and you can see here the details of this Mandelbulb. Okay, so now we're gonna minimize that and go back into our material instant here, and we're gonna see if we minimize it. I don't have a second screen right now, so grab it here and we're gonna minimize that. You can see it's minimized. It's amazing how the fractal generates this kind of pattern. You know, manually I believe it's impossible to generate that kind of details, but using the mathematical equations and using computational designing, we could generate like that type of complexity. So let's see here, and we could use the ellipse or just leave it as is. We could see the iteration. The iteration doesn't move. The iteration here controls the resolution and the step factor. Take it as a step factor. We can lower it down or keep it in the middle. Okay. Now, in order to take a shot, you could just play with the light a little bit. Like you could use light, or you could point light in order to take all the details here, and just the extra menu on the side, and click on high resolution screenshot, and it takes in just a matter of seconds. That's it. Because the real-time engines use polygon to polygon rendering, where if you heard of V-Ray and other rendering engine use pixel to pixel or pixel by pixel rendering. So I have like a default map for you. You could just use it here. Don't save. With a little bit of lighting and some cameras to use it. Okay. So you could just double click on the level and it will open up, and you could see I have put a cinematic cameras inside that, and you can use it as well. And in order to see what the camera, right click on that and pilot, or Control Shift P to pilot, and see details how the camera takes the perspective. Okay, so you could take a professional or a pro shot using the focal length here on the details of the camera. Okay, and we could use the focus settings and apply like a unique focus for that. Okay, and to see what we are focusing on, we can just click on the draw debug focus plane and see what we are focusing on. Sorry. And also you could just take these parameters here and animate this parameter. You can animate this parameter inside the level sequencer. Okay, you can animate these parameters and see how does it go with you in this cinematic filming. And all that in real time. Okay, all these assets will be available for you guys, and it's available on my GitHub repository. You can just take it and apply it and have fun with the Mandelbulb. Your voice is breaking out. Can anyone hear her? No.
No?
I cannot hear you. You guys can hear her?
No, she's breaking for us as well.
Oh, okay. Okay, honey. Okay, so how is it designed or how is it generated? It does use a C++. That's why the C++ is the native language to the processor and to the GPU processing. That's why it's better than C# or Python or whatever. C++ is a native language. So it's all in C++. If you want to see the code, just right click on that material here, Mandelbulb Mat, right click and open material.h if you know C++. And you could see a similar equation with a little bit of details and a lot of parameters to generate that Mandelbulb. So once you open it, we can define the material. This is a sample. But once you go down, you can find the code that's written there. Okay, see? Inside that material. The for loop, if you remember the for loop, the plain index, the expression material attributes, the expressions, all written inside with the for loops, okay? Does anyone have any question? Okay. Let me just port that. Let's see. You could, I believe it's they used the Mandelbulb. If you know the Avengers, what is called Avengers Infinity War, I guess. They have used the Mandelbulb effects with the Doctor Strange, I believe. I don't know. They use it in the After Effects, visual effects in movies to provide the multi dimensions or the multiverse. So they use these strange shapes, like it's jumping between realities. So these the Mandelbulb, and once we know that fractal is based on the generating pattern, we could deconstruct a pattern on our ancient history and find how is it evolved to another pattern through the nature, and try to find that formula and apply it in our design and apply it in our thesis. So this is about the fractal geometry and the fractal design and how we can take it here. Okay, so don't save. Now I would like to mention something which is the fractal learning. If you just search for what is the fractal learning, it's a strategy to make sense of complex system without getting too lost in the detail. So please read more about the fractal learning and the fractal intelligence. Deep learning. So you're gonna find a lot of articles talking about the fractal and the fractal intelligence and how we gonna control that complex and nested neural network. So please read about it and you can ask me anytime. I don't know, guys, if you have any question regarding the previous sessions, because I'm a little bit it's really concerned to move into GAN, which is the Generative Adversarial Network, and this workshop is so intensive I cannot describe or explain everything. So I don't know if we're gonna move into GAN or I'm gonna make it so simplified to you to use it inside Grasshopper. So I've started actually to make it simpler for you to train GAN inside Grasshopper. So I don't know, see, with the GAN agent and the GAN images inside Grasshopper. So I'm trying my best, but once we go to the discriminator and the generator, which is an end-to-end neural network, each network has like around the 3 to 4 convolutional neural networks. So we're talking about 16 neural network inside the generator and 16 neural network inside the discriminator, and they use the convolutional neural network, which we use this kind of behavior or kind of neural network to analyze and train AI for images. So I don't know, I left it open to see that we have like convolutional dense. We have used dense, it's to predict, it's one-dimensional. Lecky rule U, we haven't used that activation function. I don't know, I'm kind of afraid that you won't understand what is happening because we have like 2 hours to talk about the GAN and just be it. So I don't know, do you want me to give you the GAN or just use any other topic of deep learning? It's up to you. You can vote on this. The intensive AI or machine learning, deep learning from 0 to hero, it's still on the table. And it's gonna be the 30 sessions, very intensive. We're talking about 60 hours for like 2 months maybe. So we're gonna take it from like 0, from scratch, and we're gonna move gradually to the deep neural network, the up convolutional neural network, the hidden neural network, but we're gonna understand the mathematics like more purely and clearly. So that's why we're jumping over topics and we're simplifying things here, because I don't have the time to explain everything, like what is happening here. Okay, so we're loading a data set, but why we are dividing that data set by 127.5 and why we are subtracting 1. So like I have to explain everything. So this is the data set, we call it the MNIST data set, which is the hidden, which is the handwritten numbers. It's like the typical or the basic or the traditional data set over the internet for the handwritten numbers, and we're bringing it here, as you see, and it has like a patch dimension is like 60,000 with 81. Let me show you with 81 with the 28, which is the number of the pixels. You know, the X and the Y, the number of the pixels, 28 and 28. So it's the grayscale, and the grayscale goes from 0 to 255. You know the colors, the RPG, I guess. It goes from 0 to 255. So once we divide these patch by 127.5, then the range of these tensors is going to be 2. Then we subdivide, we subtract these tensors with a 1 in order to keep these tensors in the range from 0 to 1. That's what I'm talking about. It's the complexity of these things. So we reshape it again, and then we train. We construct the generator. The generator keeps generating like synthesis data or synthesis images based on the learning or based on the data set, and the discriminator decide whether these images or the data set images, yes, whether they are fake or real. So we have to construct the generator and the discriminator, and the patch, which is the size that's take under the training, okay, and the epochs. So if we go, let's try with a 200 and see how it goes. So I don't know, man. So once we start training, you could see here how it does the training. So once we start the training, so this is step 1. What's the discriminator loss, real and fake, and generator loss over these domains? Does anyone have any question until it reached the 200 epochs or cycles? Technically, it's like the core. The deep learning is the core of machine learning. Okay, we have that big bubble, we call it the machine learning, and if we go inside to the core, we have the deep learning. The machine learning have a shallow neural network, which we call it the one-headed neural network, like we've seen before. Like we have like one-headed neural network. Once we have more than one-headed neural network, we call it that a deep learning. Okay, so deep learning, it has more than one hidden neural network, okay, and different activation function. We've seen or we know the identity activation function in the previous session, which the fx equal x, the function of x equal x, it just passed through the node. But we have like different activation function, like the generator here uses the tan h activation function. So the output of the nodes must be between 0 and 1. So yes, deep learning is like more intense than just machine learning, or we call it multi-layer perceptron or whatever. It's just one layer, one hidden layer. Okay, but I don't know. When we go to the GAN, and it's the era of GAN, we've seen a lot of the products and application in GAN. We use GAN to generate synthesis data, and have you ever heard about DALE 2, and what we call it, Imagen by Google? So it generates from text to image. Yes, thank you. So this is GAN. Okay, all the picture all the pictures that are generated are fake, but they look so real. So this is the era of GAN. So we could use it in the architecture to help us predict the scene before it's rendered. Let me show you something while it's learning. So this is, we call it the super resolution. We have the like low image resolution to the high image resolution. Okay, from low image to high resolution we call enlargement, and then we could use the GAN to predict or to imagine how would our scene would be rendered. Like this is the perspective of the rhino, and here's the image that the GAN is trying to make from this. We could use like different type or different style for the imagination for that. I do recommend to submit some results for that workshop in order to help people know more about digital future and know more about machine learning in architecture. So that would be helpful. Yes, please. Yes, it is GAN. So like you see, it helps you as an architect or as a designer to like expand your imagination while you have just the conceptual masses, and it gives you like a low rendered image of your scene. Okay, so the GAN is something like you should really use as an architect or as a designer to have it always with you. Also, there's a program called NVIDIA Canvas. I don't know if you guys heard about it before. Yes, exactly. So you choose the style. Okay, you choose the style and you apply whatever you want. Like if you want to apply like a mountain, okay, then here, sorry. Uh, so if you apply like a mountain here, and then, oh, sorry, I don't know. And then you apply like another mountain, goes on and on, and if you apply just like flowers here, okay, so it starts to generate from your labeled input data. So you apply a grass, okay, and if we go to a new one, say like that, and go to the sand, I guess. and let's apply a linear line just like that. You see, and if you apply like C here, you see, and if you go like anything blah blah blah, so it's something, and you can export it as a PSD and edit it on your Photoshop. I guess it crashed, I guess. So does anyone have any question before ending this session? Do you have any like special request for the next session, because it's gonna be the final session?
Sam, if you could share some resources that we can, refer to after this workshop to learn more about deep learning, machine learning in context to architecture and design.
Especially in architecture or generally just machine learning?
I mean, specific to designing, because in general, machine learning and deep learning resources are there, but where I personally struggle is to find the right libraries which I can use in design, in architecture. So if you can refer to some resources which are more specific to design and architecture, then it'll be great. Otherwise, in general also works for us.
Okay. Would books be helpful for you?
Yeah.
Okay, awesome.
Sources that you recommend, books, videos, tutorials, anything.
Most of them are research and books. Tutorials and videos are very, very rare. That's why. Okay, I'm gonna make a folder inside the GitHub repository, and
sorry, your voice is breaking. I don't know if it's breaking just for me or for everyone else.
Can you hear me good? Oh. Can you hear me?
Sorry, I can't hear them.
Can you hear me, guys?
Yes, we do.
Okay, so I'm gonna make a GitHub folder, and I'm gonna like upload most of my books and research that I've worked on or read or discovered, and feel free to read it in your free time. It doesn't have a lot of code, let's say, but it does have a lot of like logical approach and mathematical equation that you could use. Today, the idea or the point of today to learn about the fractal geometry and how to apply like complex equation inside Grasshopper, how to write them down from just equation to numeral sentences. So you could read them, and you can try, like trial and error, try to apply what's in there. And I'm available, yeah, most of the time I'm gonna be available on Instagram, WhatsApp, or email. Just hit me anytime, and I'm ready to help you. Okay, guys. So just text me anytime. I'm going to help you. So I'm gonna show you the data set that I talked about. Not here, I guess I believe, I don't know where I put the data set for you. It's been modeler. Is it 3D GAN? I believe it's here. No. Okay, I'm gonna search for it and give it to you. I have the list ready for you for the plans that I've promised. but it's over 500 megabytes. So if you guys know any like a free hosting website that I could upload, because I don't have much of a space on my Google Drive, so that would be appreciated because it's over like 600 megabytes, I guess. So I don't know where to upload it. Okay, so the learning has finished, and you can see it just, you can generate these pattern, these GANs from the data set. Okay, so we're gonna go through it in the next session. Yeah, about the animation, I'm not gonna dive deeply in the animation of Unreal Engine, but you could use the level sequencer and just add your camera down there and take how many seconds or how many frames do you want to record the animation, or just I'm gonna explain it briefly maybe in the next session or in other session. Okay, so just search about the level sequencer. Okay, so if you guys find any like Abdurrahman says here, any like a free hosting just for a couple of days, just for a week to host the data set, and you can download it directly, and then it's okay, then we can apply the planning GAN, okay, in the Grasshopper or in the Jupyter notebook. Okay, thanks everyone for attending this session, and again I'm really sorry about the yesterday. I had like to postpone it suddenly, so all good. And like you requested, I'm gonna talk about the GAN. You can read more about it till tomorrow's session, and hopefully it would be like good and full of knowledge and entertainment for you. Thank you so much for attending, and if you have any question, just message me. Do you wanted the yes? Thank you. Do you wanted the session tomorrow or Monday? Since we shifted the third session.
Tomorrow is fine, Sam, at least for me.
Okay.
I have other commitments for the next week, actually.
So tomorrow is fine for you, right, Medha? Okay.
Yeah,
what about the others? Okay, Mahsad.
I think Monday is also good because we will get more time to practice, and if we have more questions, we can ask you, for example, during our last session.
Okay.
I want to ask you, when do you want the assignment you asked about in this session?
Anytime. It's just
okay.
Between you and me.
It's not necessary tomorrow, right?
No, not at all.
Okay.
So about Monday, is it good for you, Medha?
Sam, actually I have another class at that time, so I won't be able to attend the Monday class.
Okay, so I don't know, guys. Make like we could use it tomorrow and Tuesday. So Monday is not.
I guess maybe everyone can, if they can't make it tomorrow, then you can watch it on YouTube. So you don't have to share it 2 times. What do you think?
Okay. Okay, they are all full streamed on YouTube, so we're gonna make it tomorrow, and we could schedule a revision out of out of this workshop, a revision session later on. Okay, is it good for you guys?
Yes, yes.
Okay, then our last session will be tomorrow. We're gonna talk about the GAN and some exceptions in machine learning that we could use, and we will schedule a revision session like when's suitable for you. Maybe next week, maybe it doesn't matter. The revision session, it's out of this workshop, okay? And I'm gonna send you an assignment. Because if you want to apply for the machine learning 0 to hero, it's going to be for free. I'm not gonna charge a dime for anyone, and but I'm gonna only accept 5 participants because I'm gonna like put all my focus on for this course. Okay, so I'm gonna send you an assignment, and whoever passes that assignment successfully, it's ready to participate in the machine learning course. Okay.
Okay, I guess it's make it harder for the beginning.
It
beginner.
has to, yeah, it has to.
Okay.
But I'm gonna be free anytime to ask me any question regarding our session. But I have to make sure like the 5 chosen people are gonna be able to understand machine learning and the deep mathematical and complex mathematical equation behind it. Okay, I'm not gonna publish about this course. It's exclusively for you guys. So only 5 participants will go through that course for around 1.5 months. Okay.
Okay, thank you.
You're very welcome. Thank you, guys, and see you tomorrow.
Thank you.
You're very welcome. See you soon.
Thank you.
You're very welcome, sir. See you soon. You're very welcome, Haneen.